We've looked at thin layer chromatography and column chromatography. And in chromatography, it's essential that the things to be separated have different affinities for the stationary phase and the mobile phase. And in thin layer chromatography, just to remind ourselves, the hidden column. In thin layer chromatography, the stationary phase was a silica gel. On the surface of the silica on the surface of the piece of plastic or a glassine column, it was an inert porous solid. In the mobile phase, in each case, was a solvent, and you choose the solvent that works best, that gives the best separation. Okay, so the things with a greater affinity for the solvent will move faster and move further than the things which have got greater affinity for the stationary phase. Now we're going to look at gas liquid chromatography here today, and gas liquid chromatography, the stationary phase is again, it's an inert porous solid. But the mobile phase is a gas, and it's usually N2 or argon, and that's because they're unreactive. Don't use air because that might react with the compounds which you're trying to analyze. Now, what kind of compounds is it suitable for? It's suitable for volatile compounds. Okay, so I'm going to use this as an example today. I'm going to use methanol. Say you're trying to separate a mixture of methanol and ethanol. I found out how much each of those alcohols you have in a mixture. You wouldn't use gas liquid chromatography for amino acids, because amino acids have a very high melting point because they exist as zwitterine. So if you think most of the amino acids are going to exist, there's the R group, are going to be in this zwitterine form. That means basically when they're a solid, they've got a very high melting point because it's an ionic solid. One end of the zwitterine attracts the other end of another one. So they usually, most amino acids got a melting point of like 300 degrees C. And so you couldn't put them in a gas liquid chromatography. They would probably undergo thermal decomposition before they turn into a vapor. You've got to be able to turn them into vapors quite easily. Right, so let's have a look. If you put methanol, a mixture of methanol and ethanol into this, imagine you were trying to find out, for example, how much of those alcohols was present in methylated spirit. There's a mixture of the two alcohols. So you would inject the sample in first of all, and then that is followed by argon or nitrogen. Okay, to push it along. That's got to push it along this column. This column is very long, and I've drawn it straight here, but in reality it would be curled up to make it fit into a smaller space. And also it would be in an oven to keep those compounds as vapors. And the temperature of the oven can be varied depending on what kind of mixture you're separating. So let's color code that. Let's have the methanol. Let's do that in let's have that in red, and let's have the ethanol in blue. So you put the mixture in there, and the methanol is more volatile. It's got a lower boiling point, a smaller molecule than the ethanol, so that will have a greater affinity for the gas phase, and rather than condensing on the surface of the stationary phase. So what's happening? The gas is all the way along here. They're condensing. They're condensing, vaporizing, condensing, vaporizing, condensing, vaporizing. They're moving along like that. Okay, that's what's happening all the way along that column. So sorry, my color coding is gone. Right, so you put them in and they're all together. Your ethanol and the methanol. The methanol is going to move faster down the column. So after a certain amount of time, you'll find the methanol has overtaken the ethanol. So it's beginning to separate already. Okay, leave it a little bit further, and the separation will be greater. Here is the methanol just about ready to come off, and the ethanol is still here. Okay, so that's why the tube needs to be long. The longer the tube, the better the separation is going to be. Now you can see that the methanol is going to come off first, and it's going to be detected at the detector there. So the output of a gas liquid chromatogram, it will look something like this. Here's time on this axis, and this is the amount of stuff detected, and you get something like, well, in this case, let's see, I'll do that. That's the methanol peak coming off there, and here, let's say that is the ethanol peak. So you can see in that case, the area under this peak is bigger, so you'd have more ethanol than methanol. So it can be used to quantify as well as tell you how many different things are in there. Of course, it won't tell you what these things are exactly. You won't know what they are. The only way there's two ways you can use standards. So you could put a little bit of ethanol in with your sample, and you know where that's going to come off. And if the ethanol comes off at the same place as this blue peak, you know that the blue peak is probably ethanol. But a far more powerful technique is to couple gas liquid chromatography with mass spec. So the sample will go into a gas liquid chromatogram, and then after that it will go straight out. So you get each of these peaks going out into a mass spec. And of course, what mass spec will tell you, that will give you the MR of the compounds. Quite often, the MR of the compound is then enough to be able to identify what it is. So that is a very powerful way of analyzing volatile mixtures. So, but again, it's no good for things with high boiling points. Then you'd use thin layer chromatography or column chromatography instead.